Hello everyone, I am Dr. Navneet Kumar Lamba, Head Department of Mathematics at Shri Lemdeo Patil Mahavidyalaya, Mandhal, Kuhi, Nagpur, India. At first, I am very much thankful to the entire team of the Math Scientist Award for selecting my profile in the category of Best Researcher Award. The topic of my presentation is thermal effect under memory responses, and the topic comes under the field of thermoelasticity. So, it is required to know the basic of thermoelasticity. So it's commonly known that most material expand as the temperature rises and that growth and contraction are proportional to temperature. Thermoelasticity, an applied mathematics area, explain how temperature varies and object stretch and compress. Thermoelasticity examines temperature variations and stress mechanical deformation relationship. Several engineering sectors accelerated thermoelasticity after World War II. Exploring these topics will accelerate industrial growth and national development. As its find application in many physical processes, respected scholars worldwide are advancing the issue. One of the most significant advances in science and technology in the 21st century is thought to be breakthrough in the thermoelastic difficulties of diverse isotropic as well as anisotropic substances. Thermoelasticity developed quite quickly after World War II, driven by a number of engineering specialties. The investigation of these issues will accelerate the growth of the sector and eventually the national overall development. As we know, the material is affected thermally by temperature variation. This thermal impact includes deformation, tension, and thermal stress, thermostrate. The word thermal deformations refer to the way that temperature variation cause intramolecular stretching, which alters an object's shape and size. The body's deformation due to the stress under loaded external and internal forces is calculated using thermodynamics and well-known classical mechanics principles. Additionally, since the connection takes into account deformation resulting from both mechanical and thermal forces, it gives birth to the phenomena of thermoelasticity. The study of temperature variation and the related coupling of thermal energy with mechanical deformation in terms of corresponding stresses are the primary foci of applied mathematics discipline of thermoelasticity. This thermoelastic investigation of stresses for various metals is being utilized for the design of structural material with great stress bearing ability. Therefore, we can say that the field of thermoelasticity is very useful for the design of materials. Next, we go to the equation of thermoelasticity. Knowing the thermal distribution in an elastic body under a given system of forces and temperature requires taking into account certain physical principles, material characteristics, and geometrical requirements. The three part of solid mechanic issues, which are essential concepts of analysis, may be described as follows. First is equilibrium condition, second is condition of compatibility, third is the formula that govern stress strain analysis. Next, we go to the classification of thermoelasticity. Mainly, thermoelasticity is divided into two parts: classical theory and non-classical theory, where uncoupled theory and coupled theory comes under the classical theory and non-classical theory. In non-classical theory, there is a generalization of different model year wise, like Lord and Suleiman model in 1967, Green and Lindsay model in 1972, Green and Agdi model in 1993, Hitnarsi and Ijasik model in 1996, Chandrasekhi and Tajao model in 1998. Or in detail, we say that the heat equation, which is independent of mechanical variable, and an equation of motion which treat temperature as a known function, make up the mathematical foundation of uncoupled thermoelasticity. This hypothesis has two flaws. First, there is no relationship between temperature and the mechanical condition of the body. In second place, practical investigation contradict the parabolic heat equation implications that the pace at which temperature propagates is unlimited. To solve the first constraint, Biot in 1956 developed the idea of coupled thermoelasticity. This theory connected governing equation, solved the classical theory initial, but because the coupled theory heat equation is similarly parabolic, there is a second flaw in both theories. Generalized theories was developed to resolve this problem in order to replace the traditional Fourier law. Lord and Suleiman in 1967 first built a wave type heat equation and proposed a new law of heat transmission. A revised version of the consecutive equation was developed by Green and Lindsay in 1972. Two constants in this theory allow not just the heat equation but all the equations in the associated theory to have the relaxation paid. Particles that spontaneously migrate in response to a concentration gradient shift in concentration caused by a change in location are known as diffusing agent. It is characterized as particle migration from an elevated concentration zone to a lower concentration region. Typically, Fick's law is used to compute the concentration in this kind of applications. This is a straightforward rule that ignores the reciprocal interaction that occur when a material is put into a medium and how temperature affect those interactions. The relationship between temperature and temperature gradient, however, is somewhat correlated. Thermodiffusion occurs in elastic material when temperature, field, mass, decimation, and strain are all combined. One linked thermoelastic model was employed by Novasika in 1976. Further, we go to the fractional thermoelasticity. In last past decade, the subject of fractional order theory was found a growing field of application in hydrology, geology, mathematical biology, electronics, computer, and so on. Heat transfer equation containing fractional order operator differentials serve as the foundation of fractional thermoelasticity. The study of this problem is based on the global tendency on non-local operators. The study of ordinary derivative reflects the instantaneous response where the solution obtained with the utilization of fractional approach predict the retarded response. The study of fractional order theory mainly interpolate classical heat conduction equation like Helmholtz equation, wave equation, and diffusion equation. Here, memory impact are explored using time fractional differential operator and space fractional differential operator are designed to handle interaction across a long range. It is important to note that physics, geology, chemistry, engineering, bioengineering, robotic, and other fields have the efficiently utilized fractional calculus. For weak, moderate, and superconductivity, the primary role of the fractional order concept of thermal elasticity is to control the rate of heat transfer and the elastic propagation of waves. The primary goal of the fractional order model of thermoelasticity, in contrast to the immediate reaction anticipated by traditional theory, is to predict a protracted response to physical stimuli similar to what is seen in nature. Next, we go to the memory dependent derivative and fractional order derivatives. The concept of memory dependent derivative was introduced by Wang and Lee in 2011 by going beyond the derivative of fractionals. In fractional calculus, memory dependent derivative is a relatively new area that is being steadily gaining popularity recently. The fractional derivative, although expressed across a time, essentially capture the change that occur locally. The physical meaning of memory dependent derivative is much easier to understand than that of the fractional derivative. The kernel function mirrors the dependent weight, and the duration of memory effect is determined by the time delay. Researchers to date indicate that memory dependent derivative works better for temporal modeling Application of memory dependent derivative may be found in vibrational mechanics, thermoelasticity, thermoelectricity, and practical physics. Also, the field of hygrothermoelasticity is gaining popularity in this era. So let's discuss about the hygrothermoelasticity. In hygrothermoelasticity, the rate of diffusion grow very quickly with increasing temperature. Serve thermal aggregation caused by extremely high temperature that splits atoms and molecules apart may cause the material to melt or disintegrate. Concentration gradient may also arise as a result of uneven distribution of moisture. Heat transfer and moisture transfers are basically the same processes, and they might or might not be discussed independently based on the surrounding conditions. Irregular heat and moisture transmission through solids may alter the dimensional characteristic of structural part, causing interior stresses and strain in high performance structure. The linear symmetric flow forces connection in irreversible thermodynamics and the conservation principle in mechanics can be used to obtain the equations regulating the interdependence of heat and moisture. A number of models may be suggested depending on how physical parameters are defined. Each lead to identical equation. The only difference is how moisture intensely is regarded. Let's move to the mathematical modeling of thermoelastic problem. In order to investigate the thermoelastic effect in a solid structure, it is need to construct the heat transfer equation in the light of heat source or either without heat source by using the concept of memory dependent derivatives. We use the integral transformation approach to get the desired solution of heat transfer equation in terms of temperature function. Once the temperature function is obtained, we express or we can find out the thermal stresses, thermal deflection by solving the thermoelastic relationship. For the part of numerical computation, material property based on different metal is taken into consideration and all the obtained expressions of temperature, deflection and stress functions are plotted graphically for various time delay parameters and for the different choice of kernel functions. Further, for the formulation of heat transfer equation, we use the relationship between the heat flux vector Q and temperature gradient vector delta theta as shown in equation number 1 by using the reference number 45, Catino and Vernote. Then after Serif modified the equation 1 by applying the fractional derivative that reflect the local change as shown in figure number 2 where zeta varying from 0 to 1. And as we know, memory dependent derivative have a considerably simpler physical meaning than fractional derivative. You then modified the equation number 2 by applying the concept of by applying the definition of memory dependent derivative as shown in equation number 3. Further, Tanigawa and Komatsubara provide the heat conservation equation due to the heat source as in equation number 4 where Q is the circular laser beam moving heat source with uniform distribution, rho m is the mass density and C is the specific heat capacity. Equation 3 is further transformed into equation 4 to yield the modified governing thermal heat transfer equation with heat source under the influence of memory derivative as shown in equation number 5. Here d gamma delta theta denote the definition of first order memory dependent derivative in equation number 6. Similarly, the nth order memory dependent derivative is shown in equation number 7 where kt minus I is the kernel function and gamma denote the time delay and they are selected random to capture the actual behavior of the material. Here equation number 8 shows the choice of kernel functions based on the value of constant L1 and L2. And in general, kernel function kt minus psi range from value 0 to 1, and magnitude of the memory derivative is found less than to the magnitude of instant rate of change. And for the ease of use, further the variable is presented in the dimensionless form in equation number 9. By employing the above equation 9 above dimensionless form, the equation number 5 is reduced to equation number 10, where k is the thermal diffusion, lambda is the conductivity, rho is the density material. As a part of the statement, here we assume a rectangular plate geometry whose shape is shown in figure number 1. Here x varies from 0 to 1, y varying from 0 to b, and z varying from 0 to c. Further, all the boundary restrictions are maintained at 0. The temperature T0 is maintained at time t equals to 0, and time dependent thermal shock is administered at x equals to 0. Now finally, equation 11 express the heat transfer equation under the influence of memory dependent derivative and under a circular laser moving beam heat source, where equation number 12 to 16 shows the initial and boundary conditions. Next, the expression of thermal stresses with thermal deflection in terms of the associated moment and forces. The equation 17 here gives the relationship between the deflection and thermal bending moment, where deflection boundary conditions are expressed in equation number 18 and 19, where W denote the deflection and mu denote the Poisson's ratio. Next, equation number 20 here give the relationship between the thermal movement with respect to time, and equation 21 gives the bending stiffness of the plate. Alpha T is the coefficient of linear heat expansion, E is the Young modulus. The ensuing in-plate forces are shown in equation number 22, and by using the definition of resultant movement per unit length of the plate, equation number 23, 24, 25 are given. Also, the equilibrium equation for the movements are shown in equation number 26, 27, where Qx, Qy are the shearing forces. And equation 28 to 30 shows the thermal stresses in terms of thermal bending moment, forces, and temperature function. Here the resultant forces are shown in equation number 31. And equation number 11 to 31 here provided the mathematical formulation of the problem for a rectangular plate with the memory derivative and exposed to the laser moving heat source under memory derivatives. Once the mathematical modeling is constructed, now it is time for the solution of the thermal transfer equation first. For that we use the Fourier integral transform and their inversion formula for a finite region x0 to a is shown in equation number 32, 33. By using 31 and 32 Laplace transform, the solution of heat transfer equation 11 with initial and boundary condition given in equation 12 to 16 in Laplace domain is obtained as and shown in equation number 34, 35. Once the temperature function is obtained in the Laplace domain, it is time to calculate the bending moment and thermal deflection. For this, we are using equation 34 in equation 20 and 31, we obtained 36, 37, which is nothing but the resultant moment and resultant forces respectively in the Laplace domain. Further, using 34 in 17, the expression of thermal deflection in Laplace domain is obtained and shown in equation number 38. Further, using 36 and 38 in 23, 24 and 25, the obtained resultant moment in Laplace domain is given in 39, 40 and 41. And finally, it's time to calculate the thermal stresses using the equation 34, 36, 37, 39 to 41. In the 28, 29, 30, we get the thermal stresses mathematically in Laplace domain as shown in equation 42, 43 and 44. And referring the work as per the 49, the Laplace transform was obtained for numerical analysis purpose and deflection stresses are determined by mathematical software and graphical studies carried out further. Next, we go to the numerical computation. The computational analysis has been done for a plate with a rectangular shape made entirely of copper-based metal properties as stated in reference number 48. Here the table 1 shows the metal property with their corresponding units as well as the dimensions. As a special case, laser heating may rapidly elevate a material's temperature, causing mechanical deformation and stress. Modern space research uses laser heating for atmospheric heating and modeling, and as well as for the atmospheric observations. Copper is utilized in rocket engine because it transfer heat and may be laser heated for metal layer deposition, welding, etc. Thus, numerical computational used laser heating assumes studying copper-based rectangular plates specific material characteristic. Here, the laser moving heat source is denoted by Q in equation number 45 and equation number 46 denotes the function f of t, which is assumed as a special case. Next, graphical illustration and discussion. For each time delay parameter gamma, the numerical calculations were carried out by establishing the value of time t equals to 0.5. The flows of temperature, deflection and stress functions were observed using the numerical computational method for various time delay parameters and for the different choice of kernel functions, as well as laser moving heat source at different laser power and scan speed. As seen in the figure, the outcome are graphically displayed along x-axis. It should be mentioned that when the time delay becomes negligible and the kernel function is taken to be 1, the present thermal transfer model return to the CV model. For a range of time delay parameter value, figure 2a1 displays the temperature distribution along the x-axis. At first, the temperature function has a high value because of the effect of temperature dependent thermal shock. This value further drops when the time delay parameter goes on increasing. In other words, the more time delay, the smoother the temperature distribution. This behavior aligns with the finding in the reference 43-44, since the thermal waves are smooth, continuous and attain a steady state based on the time delay. The particles are able to transfer heat to one another with ease, which causes the temperature to drop more quickly than it would otherwise. Figure 2a2 shows how the temperature functions varies for various kernel function, forms a particular time delay gamma 0.01 value. Plotting demonstrates the kernel function significant impact on the temperature curve. For L1 L2 equals to 1, it is observed that the kernel was smoother than the kernel that was produced by setting other values of L1 and L2. Choosing a kernel function enhances the impact of memory responses and increase the likelihood of capturing the actual behavior of the content. A kernel function with a flatter curve than other may be chosen. Additionally, it is noted that temperature curve wave propagate speed is finite for various kernel functions. Next, the effect of laser power and velocity on the temperature distribution along the x-axis are shown in figure 2b1 and 2 respectively. The higher temperature measurement and temperature gradient are caused by copper based materials very high thermal diffusibility. As the power value grows, the temperature initially rises. Over time, it gradually drops toward end boundary until it reaches zero, meeting the boundary criteria. This happens as a consequence of copper's plate material losing heat over time. In other words, the heat is distributed across the plate rather than concentrated in vicinity of the laser beam. These results align with the analysis done in reference 43-44. The temperature change for different speed follows roughly the same trend as shown in figure 2b2. The reduced scan speed result in steeper temperature gradient and higher temperature peak. Thus, the temperature distribution with different kernel functions, time delay parameters, and the effects of increasing laser power and scan velocity can be used to model analysis overall temperature characteristics that are applicable to aerospace and automotive sectors. And finally, we go to the conclusion. Using memory-dependent derivative and bending moments, this work presents a memory-based model of a rectangular thermomechanical plate in the light of a circular beam moving heat source with uniform distribution. All of the behavior of the temperature and stress function results are graphically presented for different time delay parameter, different choice of kernel functions, laser moving heat source at different laser power and scan speed. The computational analysis also considered the material property of copper-based plates. When deciding on the strength of the material to prevent deformation in any type of thermostructural design dealing with high heating situation, this type of study is essential because it allows one to know the actual thermal behavior of assumed structure with different boundary constraints subjected to variation of various parameters and functions. For the material classification problem involving time delay parameter, different kernel function choice, laser moving heat source, and different laser power and scan speed, the aforementioned theoretical study is beneficial and helpful. These factors are helpful in structural design of solids for various material properties which are primarily relevant in engineering of aircraft and space research. These are the references, and again I am very much thankful to the Math Scientist Award. Thank you so much.